we introduce CELLARC, a synthetic benchmark for abstraction and reasoning built from multicolor one-dimensional cellular automata. Each episode consists of 5 support input-output pairs and 1 query, serialized in no more than 256 tokens. This compact format enables rapid iteration with small models while exposing a fully controllable task space, with explicit knobs for alphabet size $, radius $, rule family, Langton's \lambda $, coverage \text $, and cell entropy H$. We release 95,000 training episodes, plus 2 1,000-item test splits, 1 for interpolation, 1 for extrapolation. We evaluate symbolic, recurrent, convolutional, transformer, recursive, and LLM baselines. CELLARC decouples generalization from anthropomorphic priors. It supports unlimited difficulty-controlled sampling and enables reproducible studies of how quickly models infer new rules under tight computational budgets. Our strongest small model baseline, a 10 million parameter vanilla transformer, outperforms recent recursive models, TRM, HRM, achieving 58% and 32.4% per token accuracy on the interpolation and extrapolation splits, respectively. A large closed model, GPT-5 High, attains 62.3% and 48.1% on subsets of 100 test tasks. An ensemble that chooses per episode between the transformer and the best symbolic baseline reaches 65.4% and 35.5%, highlighting powerful neuro-symbolic complementarity. The leaderboard is live at CELLARC. Why do we need benchmarks like this? The RKGI challenge sparked intense interest in systematic generalization, but progress has been slower than expected. Why? First, the creative bottleneck. Even with curated tasks and automated augmentation, inventing new rule families at scale remains labor and expertise-intensive. Second, anthropocentric bias. Human-authored tasks encode incidental priors, symmetries, grid regularities, handcrafted patterns that may not reflect the broader hypothesis space. Third, compute barriers. Episodes can span thousands of tokens or require heavy program search, limiting fast iteration with small models or in-context learning. Fourth, saturation risk. As leaderboards converge, new releases demand fresh handcrafted tasks, raising cost and drifting from the original intent. Fifth, difficulty caps. Tasks are intentionally human-solvable, which sets a ceiling once models approach or exceed human performance. CELLARC solves these issues by generating tasks from multicolor one-dimensional cellular automata, a formal, mathematically grounded system that yields essentially unbounded novel tasks with tunable complexity. Each episode contains 5 support pairs and 1 query, serialized in less or equal to 256 tokens. This enables rapid training, like-for-like comparisons across symbolic and neural approaches, and sharpens the focus on rule discovery efficiency. So what makes cellular automata such a powerful substrate for measuring intelligence? Let's go back to the basics. A one-dimensional cellular automaton is defined by an alphabet of $, states, a neighborhood radius $, a synchronous local rule f, r, to applied in parallel to every cell. This model dates back to von Neumann's work on self-reproduction and computation in discrete media. Cellular automata exhibit a full spectrum of dynamical regimes, from ordered to chaotic, characterized in classical literature. We use well-defined rule families, totalistic, outer/intertotalistic, linear mod $k, and others. We steer dynamics using Langton's \lambda $, a measure of activity, which captures the order-chaos transition. These systems are not just abstract toys. They capture qualitative structure in real-world phenomena: crystal growth, snowflake morphology, fracture patterns, fluid flow textures, biological morphogenesis, and even socioeconomic dynamics. Turing's reaction-diffusion theory remains a canonical continuum account for pattern formation, and cellular automata provide a discrete, computational counterpart. In this sense, cellular automata reveal a hidden grammar of nature, an abstract language through which diverse systems express their underlying order. Now, why are they ideal for benchmarking generalization? Here are 5 key properties that align perfectly with our design goals. 1. Calibrated complexity. By varying $, R$, rule family, and \lambda $, we produce smooth difficulty gradients, from additive dynamics to chaos. Empirical cell entropy, H$, provides a data-driven summary of regime complexity. 2. Finite local hypothesis class. Each update depends only on a window of size 2R plus $1. This yields a compact, structured search space, ideal for both symbolic solvers, e.g., de Bruijn analyzes, and neural models that can exploit locality. 3. Exact measurability. Because the rule is formal, we can exactly compute which neighborhoods appear in supervision, using de Bruijn constructions. We report \lambda $, H$, and \text $, replacing opaque difficulty labels with reproducible diagnostics. 4. Unlimited instances under short contexts. CA histories admit infinite episodes while keeping supervision compact. By constraining k in \2, \dots, 6 $, and r in \1, 2, 3 $, we span low to high entropy rules within token budgets suitable for efficiency-centric evaluation. 5. Mathematical symmetry. CA are translation equivariant and time homogeneous. The same rule applies at every site and step. Many families admit additional symmetries: reflection, state relabeling, additive structure, enabling targeted tests of systematic generalization. We leverage all of this in CELLARC. Episodes are sampled across families and \lambda dollar regimes. Difficulty is controlled via $k and \textcov dollar. And evaluation focuses on how quickly a model infers the hidden rule, not just whether it eventually does. Now let's walk through the dataset. The CELLARC 100K dataset contains 95,317 training episodes, 1,000 validation, 1,000 for interpolation, 1,000 for extrapolation. All episodes are less or equal to 256 tokens long, with a median flattened length of 156 and a maximum of 256. Each episode has 5 support pairs and 1 query, generated by unrolling a CA and extracting patches separated by a fixed step size. The key innovation: coverage-aware resampling. We ensure that the 5 support windows collectively cover the query with query-weighted coverage \textcov, \jec0, $5 in training, while avoiding leakage. The query solution is never copied into the supports. The TSDXDRAPOLATION split is deliberately constructed to be the hardest. It contains only chaotic episodes, 100% in the high $\lambda bin, with low coverage and high entropy. This creates a clean separation between 2 forms of generalization. Interpolation: performance on unseen instances from the same distribution. Extrapolation: robustness to systematically harder, lower supervision cases. Across splits, the mean episode length is tokens, well within our 256 token budget. The distribution of rule families varies significantly. Training data is balanced, ~25, 5% random, ~24, 1% totalistic, and others. But the extrapolation split concentrates in totalistic 86.8% and linear mod $k 9.4%. Rules: due to the high $\lambda, high $h filtering. This means extrapolation scores primarily reflect generalization to these 2 families in the chaotic regime. Now, how do we generate these episodes? We follow a 4-stage pipeline. 1. Raw pool synthesis. We sample CA across K \in \2, \dots, 6 $, R in \1, 2, 3 $, and various rule families. For each rule, we generate 5 support pairs and 1 query using cycle, unrolled, or hybrid constructions. We draw a raw support span coverage target uniformly from $, then sample support spans accordingly on the de Bruijn cycle, ensuring diversity. This stage yields raw episodes. 2. Filtering and enrichment. We downsample to ~110, 000 high-quality episodes, enforcing fingerprint-level deduplication. Novelty of the query solution: flattened supervision less or equal to 256 tokens. We balance over a 2D histogram of \lambda and observed coverage. Degenerate rules, e.g., absorbing states, are removed. Each surviving episode is replayed at fixed width and horizon to compute enriched descriptors: \lambda, h$, mutual information, morphology stats, and inline rule tables. 3. Coverage-aware resampling. To avoid unsolvable episodes, we rewrite support windows so that the 5 supports cover the query with \textcov, \jec0, $5, while avoiding leakage. Episodes that can't satisfy this constraint are dropped. This leaves us with ~95, K 100K compliant episodes. 4. Splits and packaging. TSDXDRAPOLATION gets the most challenging cases: lowest \textcov dollar, highest \lambda, highest h$. It's 100% chaotic by \lambda bin. The rest are shuffled deterministically into train, validation, and TSDINTRPOLATION, with similar distributions. We also sample 100 episodes from each test split for cost-effective LLM evaluation, since full 1K splits can cost hundreds of dollars. All data is available in JSONL and Parquet formats, with mirrors on Hugging Face. Exact generation commands are in the repository. Let's clarify the key difficulty knobs. Alphabet size $k, uniform over $, balancing binary rules and higher entropy palettes. Radius R$, most mass on R equals $1, ~70%, with tails to R equals $2 and R equals $3. Temporal horizon $t and window size C equals 2 RT plus 1, indirectly bounded by the 256 token budget. Rule families: cycle, unrolled, hybrid, encompassing random, totalistic, outer/intertotalistic, threshold, linear mod $k, and dense tables. Complexity and dynamics: filtering and split assignment operate on \lambda and h$, covering ordered, edge of chaos, and chaotic regimes. Query-weighted coverage \textcov. Supports are rewritten to cover the query with \textcov, \jec0, $5 in training, but TSDXDRAPOLATION collects the lowest coverage items. Our primary metric is token, hamming, accuracy on the query length. We report it separately on interpolation and extrapolation, and summarize generalization with the interpolation, extrapolation gap \delta $. Now, how does a model actually solve a task? Each episode is structured as 5 input-output pairs. 1 query input. 1 solution output. The model sees the 5 supports in the query input, but not the solution. It must infer the underlying rule and predict the next step. We evaluate 2 training interfaces. 1. Task embeddings TE. Each episode shares a learned task embedding e/text step $, injected as a broadcast bias at every time step. This allows memory-efficient training, no need to co-present all supports. 2. In-context learning ICL. The full episode is serialized into a single token stream. X1 X5 5 QXTM MYE. Loss is applied only on masked query positions, using teacher forcing during training. This interface naturally handles unseen tasks, at the cost of higher memory and sequence length. We evaluate a broad range of baselines. Symbolic. Copycat echoes the query input. Most frequent, predicts the most common color in the episode. Random, samples uniformly from the observed palette. De Bruijn local map, learns a local rule F. C/$2 by counting windows, applies majority backoff for unseen windows. We also report an oracle ensemble. For each episode, select the higher accuracy between the transformer T and De Bruijn solvers. This is not deployable, but it quantifies headroom for learned selectors. Neurals. Vanilla transformer, encoder only with task embeddings. LSTM, encoder only with optional task embeddings. 1D CNN, dilated convolutions with residuals. Neural CA, 1D neural cellular automata, but we'll come back to this. Recursive reasoning models. TRM and HRM, based on Jellicoe-Martineau 2025 and Wang et al. 2025. All use adaptive computation time, ACT, rotary embeddings, RMS norm, SWI glue, and a halting head. LLM baseline. GPT-5 High, evaluated via in-context prompting, no fine-tuning. We use the OpenAI API with reasoning effort set to high. Now the results. The strongest open model is the vanilla transformer with task embeddings, achieving 58% on interpolation and 32.4% on extrapolation. This exceeds the best symbolic solver, De Bruijn, 52.5298, clears trivial baselines most frequent, 50.4282, and beats all other neural architectures. Even on extrapolation, where coverage is low and dynamics are chaotic, it outperforms CNN, LSTM, and recursive models. CNN and LSTM lag the transformer by -5.7 points on interpolation and -2.4 on extrapolation. Recursive models, TRM, HRM, transformer ACT, remain competitive but fall behind, especially when task embeddings are used as a prefix token. In fact, ICL often generalizes better than TE for recursive models, suggesting that task embeddings can act as shortcuts, encouraging overfitting. The De Bruijn local map is a surprisingly strong baseline. Its accuracy closely tracks \text $. Where supports tile the query, symbolic lookup is hard to beat. But as coverage drops, the transformer benefits from structural priors, like totalistic symmetry, and soft interpolation over partial tables. This reveals a key insight, neuro-symbolic complementarity. An oracle ensemble, selecting per episode between transformer T and De Bruijn, reaches 65.4% interpolation and 35.5% extrapolation. This is an upper bound, but it shows that the two approaches fail in different ways. On interpolation, symbolic wins when coverage is high. On extrapolation, the transformer and LLM win when coverage is low. Now the closed LLM, GPT-5 High, achieves 62.3% and 48.1% on 100 task subsets. It surpasses all trained small models, especially on extrapolation. Why? Because broad pretraining appears to amortize search over rule families, allowing the model to recognize or infer local rules even under low coverage and high entropy. Family-wise analysis shows GPT-5's edge comes mostly from strong performance on linear mod $K and threshold rules, where the vanilla transformer lags. This gap is a major open challenge. Can compact open models match this robustness? What do these results tell us? A sufficiently expressive sequential model, like a vanilla transformer with task embeddings, can infer CA rules more effectively than architectures explicitly designed for iterative reasoning. Global attention can emulate local updates without committing to a fixed receptive field. Task embeddings, when implemented as an additive bias, help bind the 5 supports into a coherent latent rule. But when injected as a prefix token in recursive models, they can become shortcuts, leading to overfitting. We see this in the training dynamics. Recursive models drive training loss down, but validation loss peaks early and rises, a classic sign of overfitting. Meanwhile, the vanilla transformer shows smooth, stable convergence. So what does CELLARC actually measure? It's a controlled test of rule discovery efficiency under partial local information. Each episode compresses to less or equal to 256 tokens. The hypothesis class is finite and explicitly local. The primary source of difficulty. How much of the query's centered windows are covered by the supports? This isolates a clean question. Given 5 supports that reveal only a subset of length $C neighborhoods, can a model infer the hidden local rule well enough to label the query? And what drives difficulty? Across all models, Accuracy increases with \text cov dollar and declines with higher \lambda dollar and h dollar. Higher coverage shrinks the unobserved slice of the local map, making majority or backoff strategies viable. Higher activity and entropy increase the diversity of relevant neighborhoods, amplifying the penalty for unseen windows. This confirms our design. TESDXDRAPULATION is a sharp stress test, not just of model capacity, but of robustness to partial information. And what does this mean for the future? CELLARC is not a complete measure of reasoning. It's one-dimensional, local, and focused on rule discovery. But that's deliberate. It's a microscope, not a telescope. It enables fast, reproducible, efficiency-centric studies of inductive biases, scaling laws, and architectural trade-offs. It supports comparative evaluation across regimes. TEVs ICL, symbolic Vs neural versus mixtures, compute scaling at fixed budgets. And it's cheap to iterate on. Future directions. 2D multicolor CELLARC, with matched metadata and coverage controls. Noise robustness, token corruption occlusions. Multi-query variants, to test continual inference. Richer automata, Mealy machines, subsequential transducers, universal Turing machines, to probe stateful computation, alignment, and unbounded memory. Meta-learning, using episodic sampling as tasks, enabling controlled studies of fast adaptation. And we're already exploring these with the community. In conclusion, the path to general intelligence requires systems that can rapidly acquire new tasks from minimal supervision. CELLARC isolates and measures one fundamental skill, inferring local rules from compact, partial observations. By grounding task generation in cellular automata, not human intuition, we obtain a benchmark that is controllable, generative, efficient, transparent. It gives us explicit knobs, k dollar, r dollar, \lambda dollar, h dollar, \text cov dollar. Episodes serialized to less or equal to 256 tokens, enabling fast iteration and apples-to-apples comparisons. It reframes performance as rule discovery efficiency under partial local information, with measurable difficulty, not anecdotal, hardness. Empirically, a compact transformer with task embeddings is the strongest open baseline, outperforming recurrent, convolutional, and recursive models. The Bruijn solver remains a formidable symbolic competitor, especially when coverage is high. And a closed LLM, GPT-5 High, further improves on extrapolation, suggesting that broad pretraining amortizes search over rule families. But the gap remains, and that's where the real challenge lies. We release the data, code, and live leaderboard to encourage rigorous, efficiency-centric studies, neural, symbolic, and neuro-symbolic. In our view, CELLARC complements RKGI by serving as a microscope for one recurrent capability at the heart of harder tasks, learning compact rules from scant evidence. We invite the community to use its controllable knobs and rich metadata to build better selectors, close the linear mod $k gap, prototype open models that match LLM-level robustness under low coverage. As a practical instrument for rapid, transparent iteration, CELLARC moves us a small but measurable step closer to systems that can acquire new structure as quickly as they can recognize it.